Okay, we're going to get started. I believe this is our last colloquium of the semester. Jack is nodding his head yes. Great. And we're very fortunate to have Allison Kirkpatrick here to tell us about the latest, greatest stuff from the JWST satellite, or I guess it's not circling anything. Well, anyway, fine. As you may know, if you were alive last July, the first images from JWST were released. I believe President Biden was so impressed with them that he sort of co-opted the press release the night before it was supposed to happen and showed, in fact, an image from one of the deep surveys, which I expect you will tell us about. And since then, whenever I've traveled anywhere, all anybody wants to know about is what we're learning from these JWST images. So when Laura said to me, who would be good to talk about JWST, I said Allison Kirkpatrick, who was a YCAA prize postdoctoral fellow here from 2016 to 2018. And she's involved in multiple JWST programs, including the CEERS program that is, I think, the extragalactic survey that got the most papers out the most quickly. So I'll let her tell you about that, all that instead of me. But let me just say that a little background. Allison was an undergraduate at University of Florida, majored in mathematics, which I only learned recently by looking at your CV, mathematics, and then went to graduate school at UMass, where she worked with Alexander Pope. And she is well known as sort of the world expert on disentangling the different emission components in AGN, separating the star-powered light from the light due to black hole growth. And that I expect will also play into what she's going to tell us. But anyway, I'll let her tell us the secrets of the invisible.
Okay. All right, great. Thank you. Thank you so much for having me back here. It's great to be back at Yale. So I was here from 2016 to 2018. And so I'm going to talk about my work with the Cosmic Evolution Early Release Science Team, or CEERS. As Meg mentioned, yes, we've had the most papers the most quickly. This is because we got the first data with the telescope, and it is public. So we had to put out our papers before we were scooped. All right, so just a general, well, we're going to see if my clicker works. No. Yeah, we're going to unplug and plug and hope that works so I don't have to not tied to a computer. Okay. I just changed the batteries in this and nope, it's okay.
Just have to click on the slide.
Yeah, I know. Okay, all right. So I want to start with a multi-wavelength view of the universe, just to give you a flavor of why we have different telescopes that view things at different wavelengths. So in the high energy universe, so that would be over to this side of the plot for those of you on Zoom, looking at the higher frequencies. This is really the work that Meg does. We can see unobscured phenomenon. So every galaxy is forming stars, every galaxy has a black hole at the center, and at the higher energies, we can directly view the accretion onto black holes, and we can directly view young stars. However, galaxies have this pesky property, and that they have dust in them. And dust obscures these things. So dust preferentially obscures higher energy phenomena. And so if we really want to untangle what's happening in galaxies, we need to look in the infrared, because it's there that we can view obscured star formation and obscured black hole growth. Now, there's another pesky property of the universe, and that is that it's expanding. And so as the universe expands, the wavelength of light that is being emitted by galaxies is also expanding. So as we move into the higher redshift universe, what happens is these unobscured phenomena, the wavelengths that we want to observe them at, get stretched out. And so they are also in the infrared. So infrared telescopes are really powerful for obscured phenomena and for unobscured phenomena. So just a quick rundown of what is on James Webb. So you can see that James Webb is a lot bigger than Hubble. This is great because we need photons. We want to see faint galaxies. Faint means far away, and typically. And to do that, we need a lot of photons. So we need a bigger collecting area. A bigger collecting area also gets us a lot better resolution. So our previous generation of infrared telescopes were much smaller. So they just didn't have the angular resolution that James Webb has. They're not going to be able to see faint details, and they're not going to be able to resolve out structure within galaxies. James Webb has 4 instruments on it. I'm going to talk about 3 of them. Well, if we're lucky, we'll get to the mid-infrared instrument. MIRI is mid-infrared. It does both imaging and spectroscopy. NIRCam does near-infrared imaging. This is where we're going to spend most of our time. And then there are 2 infrared spectrographs on here. I'm going to talk about NIRSpec. All right, so just to tell you a little bit about my time at Yale, the CEERS collaboration and the discoveries that I'm going to talk about today, we actually wrote that proposal in 2016 when I was here. What happened is James Webb got delayed a lot. So I remember it was 2018. I was sitting there writing a proposal. We had proposals due in 4 days. And we got a press conference that happened. And they told us James Webb is going to be delayed for 2 years. And we're all like writing our proposals that are due on Friday. And I believe I and the rest of the infrared community collectively got up from our desks, and I went home and I drank a bottle of wine at like 11 a.m. While we were waiting for this to happen. Why so many delays? Well, James Webb is incredibly complicated. This thing is the size of a football field, and it has to unfold in space, okay? Because you don't have rockets that are the size of a football field, so you have to fold it up and unfold it in space. Not only that, while it's unfolding in space, it is also traveling beyond the moon. So it is stationed at our second Lagrangian point beyond the moon. And it takes about a month to get there. So there's no servicing it if it goes wrong. So we need to be really careful. We got to get it right, guys. So it launched on Christmas Day, 2021. And yes, I was up watching the launch at 5:30 in the morning, along with the rest of my team. Unfortunately, I'm not going to show you a video of that. It was really crowded and cloudy in French Guiana when it launched. And so you really can't see it very well. But launch went really, really well. As many of you have asked me about, what is the life expectancy of James Webb? 20 years because of how well launch went. Okay, so this is a $10 billion instrument beyond the moon, and it's going to last for 20 years. Well, why? Why did we do this? Obligatory astronomy slide for every astronomy colloquium. We have the history of the universe. Okay, it all started with a bang, and then we get to the dark ages. Dark ages happen at a redshift of 20. And for those of you in the audience who don't think in redshift, I have the years up there as well. Redshift is referring to basically how much light is being stretched out. So it has to do with expansion. And then, you know, the early universe is expanding. These galaxies are farther away from us. They're expanding more than the local universe, so you get longer and longer redshifts. All right. One of the main questions, Cosmic Dawn, is when did the first galaxies in the universe appear? Not only when did they appear, but what did they look like? After that, we get the epoch of reionization. In the primordial soup of the early universe, you had free streaming electrons and free atomic nuclei. As the universe cooled, these electrons joined to the atomic nuclei, and you get recombination. And of course, this forms the cosmic microwave background. However, okay, so all your hydrogen is neutral. Today, in our universe, all of our hydrogen is ionized. How did it get ionized? Well, that happened in the epoch of reionization. And what we want to know is what galaxies are responsible for reionizing the universe. Was it just a few of them or very specific ones? Could every galaxy do it? This graph is also misleading because it shows the epoch of reionization being really quick. It wasn't. It lasted over several redshifts. Then we get to cosmic noon. Cosmic noon is around redshift of 2, so about 10 billion years ago. This is the epoch of the universe when galaxies were forming their most stars. This is the epoch of mass buildup. So most of the black hole mass, most of the stellar mass was formed at redshift of 2. Today we're slowing down, if you will. I like to say that we're at cosmic happy hour. And things are going to continue winding down. And so what we want to know at redshift of 2 is, when did galaxies get their structure? So today we have disk galaxies, we had elliptical galaxies. When did that happen? And what is the specific interplay of the physics within galaxies? Galaxies have 2 major components that contribute to their heating: your supermassive black hole and your stellar mass. How do those 2 things together drive galaxy evolution? All right, so we're going to start at cosmic dawn. This is the universe prior to 550 million years old. Yeah, and we're going to start with the Hubble Deep Field. This is not James Webb. Don't ooh and ah over this image. Okay, this is the Hubble Deep Field. This image was taken in 1995. This is the motivating image for the James Webb Space Telescope. Okay, this is really the beginning of probing the beginning of the universe. And this image is smaller than the moon, so it's actually more like this cyan square here. There's various Hubble fields compared to the size of the moon. So it's very, very small. And it actually has the record holder up until what I'm about to tell you about for the most distant galaxy in the universe at a redshift of 11, or about 400 million years after the Big Bang. And this galaxy has been spectroscopically confirmed. I mentioned this galaxy because some of you might know this was work done at Yale by Pascal Oesch, who used to be a YCA fellow here, and Peter Van Dockum. All right. So this image took 100 hours to make. Well, in 2004, did it again, pointed a telescope at a blank patch of the sky and found 10,000 galaxies there. Prior to these images, astronomers didn't really know how many early galaxies they were going to see, or how far back they even could see. And so these images were gambles. And this one took 11 days to make. Making an image like this, what you do is you image your sky in one specific filter, so one wavelength of light, and then you combine them all to get a color image. So each filter had about 96 hours of integration time. So you're leaving your shutter open for 96 hours. And you're doing it again and again and again. So this is 10,000 galaxies. What is crucial about this image is that it's in the taken in the optical and the ultraviolet. That's going to really hamper how far back we can see for reasons I'm going to show you in just a second. Okay. All right. So we have these Hubble deep fields, and they really motivate the question, how far back can we see? Because every time we open our shutter for longer and longer, we see further into the universe than we thought we would. So what is the edge? James Webb is designed to answer that question. It is a first light instrument. It is designed to answer it in 2 ways. Number one is at the right redshift, or the right wavelength to see high redshift galaxies. And number 2, it just has such a much bigger light collecting area. So this is one portion of our CEERS field. And in this field, we've already found at least 5 galaxies at higher redshift than Pascal's galaxy. This image took 7 hours, and that's less than an hour per filter. It's 3,000 seconds per filter. And we already have much deeper view of the universe than I've showed you. And what's critical about this field is that this is the same size as the Hubble Ultra Deep Field, but it is so far 1/8 of what we've actually taken. And we're getting our other half. This is only half of our data. We're getting the other half this month. So already we just have much wider area and we're going deeper. And we haven't even warmed up yet. This isn't even our deep program. We have a deep program that we're going to go for several hours more than this. So we are going to find that edge. We are going to find the first galaxies.
Question here.
Yeah.
Can you show the previous slide? Yeah. So when I look at this, I cannot separate it from any other picture I've seen. If you see it, can you tell how far back it was?
Yeah. No, I'm going to show you how we tell. Yeah, just by looking at it, unless you're an expert, I don't expect you to know. I'm going to show you how we know. Yeah. Okay. 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 Yeah. Okay. All right. So here's an example of one galaxy. Actually, can we leave the lights out?
Yeah.
Are you guys okay with that? That way I can't tell how many of you guys are going to sleep. Oh.
Takes a minute.
Okay, great. Yeah, I know you guys, New England is so freaking depressing during colloquium because you can just watch the sun go down. It's like dark afterwards. Okay, so this is an example of one galaxy. The JWST filters are on the bottom. So again, each filter is shown. So we're taking the picture of the galaxy in multiple filters. The filter names correspond to the wavelength. So F115W means that it is taken at 1.15 microns. So 150 is 1.5 microns. The W just tells us the size of the filter. And up top, you can see Hubble. So you can see this galaxy compared to Hubble. And then over here, we can see Spitzer. So Spitzer was our previous generation infrared telescope. And the images are actually lined up with the wavelength that they correspond to. And then this was in a paper, so we have our predicted redshift up there, but that's okay. I'm going to walk you through how we got that redshift. So you can see that this galaxy is actually not visible in Hubble at these wavelengths, but it is visible in James Webb. That is due to the increased sensitivity because James Webb is so much bigger. And then you can see that it looks like complete garbage in Spitzer, but you can actually see something in James Webb. That is because you have a much bigger mirror, so you're getting higher angular resolution. All right, so how does this help us? Galaxies are made of stars and they're made of gas. And most of that gas is hydrogen. And as you all know, hydrogen will eventually be ionized if you hit it with hard enough radiation. Okay, so that occurs at the Lyman limit of the system. So that occurs at 912 angstroms. If you hit a gas cloud of hydrogen with a photon that has a shorter wavelength than 912 angstroms, it has enough energy to ionize some of that hydrogen. Okay, you hit it with a lot of photons, you're going to ionize a lot of hydrogen. What ends up happening, though, is that means that those photons aren't escaping your gas cloud, so you can't see them. Young stars are producing a lot of UV radiation. So we can directly see the light from young stars at wavelengths longer than that Lyman limit, but at wavelengths shorter than the Lyman limit, all of that light is being absorbed, and so you're not going to see it. So if we can find that Lyman limit, we know where the galaxy is located, because as we move back in time, your light is being redshifted, is being stretched out by the cosmic expansion. So when we move really far back in time, that Lyman limit occurs in the infrared. Makes James Webb the perfect telescope to find these high redshift galaxies. And I know this was a cute little cartoon, but the real thing looks pretty much just like it. Okay, these are our two highest redshift galaxy candidates at Z greater than 12. And you can see at these really short wavelengths. Oh, okay, lovely. Okay. These really short wavelengths, you don't see anything. You don't see any emission because all that emission is being absorbed by the galaxy itself. these much longer wavelengths, you're seeing the integrated emission from all the stars in the galaxy. And then we can fit that with a model. I am, for the purposes of this talk, not going to talk about the orange model. The correct model is the blue model. And that blue model models exactly where the Lyman break is supposed to be. And it tells us the redshift of the galaxies. So we have done this in our whole CEERS imaging. What?
Sorry, what are the times years after Big Bang for the
I didn't calculate it. I didn't calculate it. So 16, let's think. Redshift 16 has to be like 180 million years after the Big Bang. Okay, so 180 million years. So this brings up a good question, right? Which is that the previous record holder was 400 million years, and now we're at 180 million years. And you might say, what's a few hundred million years among friends? But it matters a lot, as people like Frank can tell you, it matters a lot for how quickly you can form your dark matter halo. And I'm going to talk about that on the next slide. Okay, so we've done this survey. So now we have a whole bunch of galaxies, and we can make a luminosity function. So I'm going to walk you through this because it's a very technical plot. First of all, on the bottom is UV magnitude. And I don't think I have any optical astronomers in the room, which is good because then I can tell you that magnitudes are stupid. So magnitude corresponds to brightness. So we are looking at, on this end is the bright end. And what you are seeing on the y-axis is the number of galaxies. You can just think of this, it's technically the number of galaxies in a cosmic volume. You can think of it as the number of galaxies. So what luminosity functions tell us is basically how many bright galaxies you have and how many faint galaxies you have. And so you should pretty much always have more faint galaxies than bright galaxies. Nature turns out to really love a log normal distribution. So the faint things are really, really populous. So we had detected 26 galaxies at Z greater than 9. So we were able to build on the luminosity function. Our point are the red points, and then various other surveys are shown at slightly lower redshifts with the different other points. But the question here is, how does the luminosity function change with redshift? So that's what's shown on this plot. We have measured the luminosity function at much lower redshifts, so much later times in the universe. And that's what all the blue lines is, the luminosity function at much later times. And so we can use a forward modeling technique, and we can evolve that, and we can predict what the luminosity function should look like at these really, really early times. So that's shown by the gray, and the two different slopes correspond to two different models. And you get the gray. Okay, but what you'll notice is that our galaxies are all at the top end of the prediction. So they're all at the top of the gray region. And what that means is that the luminosity evolution is slowing. So in other words, we are seeing more brighter galaxies earlier than we thought that we should. How do you get galaxies this bright this early? This is a bit of a problem, okay? Because what happens first is dark matter has to collapse. The dark matter structures in the universe formed before the galaxies did. So we can actually turn this into a dark matter halo mass, and I put this next slide in basically just for Frank and Daisuke. But so we can look at a cosmological simulation, and we can do abundance matching. So the way that you do this is you assume that every galaxy of a certain brightness are all going to lie in the same mass halo. So if you have a galaxy of a magnitude of -20, then it's going to have a certain halo mass, and the same is true for all galaxies. And so then you take a cosmological dark matter model, and you figure out how many galaxies you have of a certain brightness, and then you'd say, oh, we also have this many halos at this mass, so these are the types of halos that these galaxies lay in. All right, so we've done abundance matching, and we have found that our galaxies at a magnitude of -20, which again, you can just think of it corresponds very directly to a mass and to a star formation rate, should all lie in halos with a mass of more than 10 to the 10 solar masses. Okay, great, that's good. Now we can do that forward modeling technique again. We can look back in time or look forward in time, and we can figure out what kind of halos these galaxies will eventually lie in, and we can back out and we can predict, we can make a prediction. Looking in the very universe, in the very early universe, dark matter halos at 10 to the 10 solar masses, so right here on the plot, that's the gray, should have hosted galaxies that are this brightness. So almost -19. Instead, what we found is that they host galaxies at a brightness of -20. Magnitude systems are backwards. So -20 is brighter than -19. I know. And so these dark matter halos are hosting brighter galaxies, which could mean more massive galaxies than we thought that they should. This tells us something, again, about how either baryonic matter streams into dark matter halos, or it could also tell us something about the mass to light ratio in galaxies. Because the hard part about astronomy is that all we are ever looking at is light. We're never directly measuring physics. We're measuring light, and we're trying to get physics out of it. And so we have mass to light ratios where we look at light and we assume how massive a galaxy is. That is based on how many stars galaxies form today. But in the early universe, they probably formed more massive stars than they did today. And so that mass to light ratio is going to be different. All right, so that is something that is a current tension. This prediction, the observations not agreeing with predictions, we don't have a great answer for it just yet. Yeah.
Are there air bars?
No. Why do you want an error? It's perfect. No, there's no error bars on the forward modeling technique because we didn't assume any uncertainty. We assumed that our halo mass relationship was perfect, and just.
There are some error bars on the observation that can be propagated.
Not on a magnitude. No. Our magnitudes are like the errors are within the data point themselves. Like they're very, very small. These are all signal to noise ratio of like 20. So I don't know. We can talk about this at dinner. Okay. Okay. So now let's turn to the epoch of reionization. Okay. Next up is Joe Biden's image. It's the one over here. Okay. This was the worst. So astronomers found out about this the day of, because the big press release was supposed to be on a Tuesday, and we found out the day of that Joe Biden wanted to release one of our images. And so then we all tuned in for the press conference, which happened like it took like an hour and a half late. And then they didn't show the image on a screen. I don't know if you guys watched this. It's literally Joe Biden putting up a cardboard poster of this image on an easel. Like, this is $9 billion for this. So then the following day, we actually got an image that could be downloaded and played with. So this is the SMACS cluster. I don't know what it stands for. And this one is Hubble next to it. This is a beautiful cluster because it is lensed. And so these two dots here, this is the foreground cluster. And all of these bent galaxies are way in the background. And so what you are looking at here is basically all of the dark matter in this cluster is acting as a lens, and it is changing space-time, which we know thanks to Einstein. And so as your photons from very distant galaxies travel to your telescope, they also get curved in an arc because they have to follow that path of space-time. And this is really, well, in some ways it's helpful because these galaxies get brighter, and so they're easier to detect. In other ways, it's unhelpful because then it's very difficult to see their shape, their true shape. Okay, so SMACS had some of the first spectroscopy. So this spectroscopy was taken with NIRSpec, is a multi-object spectrograph. It's got these little micro shutter arrays. This is what it looks like. So this is what the spectrum itself looks like when it hits the detector. And then you take it and you turn it into this through magic. And this is mind-blowing. This is a galaxy that is at a redshift greater than 5. Hubble does not have anywhere near this kind of spectroscopic capabilities. Hubble has a GRISM on it, and it's really, really bad. And so it's difficult to get any kind of usable spectrum. But NIRSpec did this again very, very quickly. And so we were able to get these spectra for 5 galaxies at a redshift greater than 5. And that let us measure their emission lines. And we can change that into learning something about their ionization or their radiation field within the galaxy. So O3 is a forbidden transition. So you need really, really good ionizing radiation, a lot of it, to be able to see these kind of emission features. Whereas H beta is your standard run-of-the-mill hydrogen transition that you see in star forming regions. And so we can make an ionization plot. And so on the y-axis and on the x-axis, we are comparing the strength of these high ionization lines to the more standard hydrogen lines. Okay, so ionization increases with the arrow in the plot, and ionization essentially tells us how many high mass stars are being formed, because your high mass stars are the ones that are responsible for all of the ionizing radiation. So if we can trace ionization, we can figure out how many high mass stars are being formed. And then we can also measure metallicity. Metallicity follows the curve. Astronomers have hydrogen, helium, and then metals. Everything else is metal. Metals tell us about the star formation history of a galaxy, or the chemical enrichment, okay? Because again, the Big Bang is responsible for hydrogen and helium. Everything else, including you and me, were formed in the inside of stars. So you have to go through a few generations of star formation to get metals, to get a high metal content, okay? Our galaxies are the 5 red stars. So they have very, very, very hard radiation fields. So a lot of ionizing radiation, and they have low metallicity. The one, we show some different comparison samples. The one that I really want to draw your attention to are the gray triangles down here. All right, that's not a triangle, that's a diamond. Okay, whatever, this isn't a geometry talk. It's the gray diamonds, okay. The reason I want to point those out, those are green peas. So that is a green pea galaxy. Like, it's called a green pea galaxy because it really is green and pea-shaped. These are actually in the local universe, so well, a redshift of 0.1. The reason these are so important is because these are thought to be local analogs for the kinds of galaxies that re-ionized the universe, because these also have a lot of ionizing radiation. But the trick is, because remember, your ionizing radiation can hit your hydrogen within your galaxy itself and be absorbed. To re-ionize the universe, you need to get your ionizing radiation out of your galaxy. So you need to have a high escape fraction, or a lot of photons leaking out. Green peas do. But these galaxies are our SMACS galaxies, have more ionizing radiation than the green peas do. So it's possible that you don't need really high photon escape fractions if every galaxy in the most distant universe has really high ionization fields. The other thing that we can look at is the mass metallicity relationship. So again, metallicity, how much not hydrogen and helium do you have? Mass is a measure of how many stars you have. These things should be linked, because stars are responsible for metals. So as you build up your stellar population, you should also build up your metallicity. So what is being plotted here is the stellar mass of our galaxies versus their metal content. Higher metal is higher on the plot. Okay, we measure metallicity through this really weird parameter, but high metallicity is up towards the top. And then these are the relationships, the lines on here are shown, are the relationships that have been measured in the more near universe at lower redshifts. And then this is the prediction for what you should see at Z of 7, okay? But we don't see that. These things are higher. These things, some of them are low. Some of them agree with this prediction of how few metals you should have. But a lot of our things are low mass, but they have high metal content. Okay, so again, this is evidence for very quick chemical enrichment. So maybe they form stars faster than they previously thought. Also, interestingly, the high metal content is good evidence for the amount of dust in these galaxies. There has long been a prediction that after redshift 3 or so 12 billion years in the past, prior to that, you really shouldn't have much dust. Most star formations should be unobscured because you haven't had time to form dust. And that is what is leading to designing telescopes like James Webb, designing telescopes like the successor to Hubble, is this assumption that there's just not a lot of dust in these galaxies. Some observations with ALMA point to the case that that isn't actually true. And this does too. If we see really high metal content in these early galaxies, they could have a lot of dust, and we would be getting only half the picture if we look at them, if we just look for unobscured star formation. All right, so let's go back to pretty pictures. All right, so let's talk about what these galaxies look like. This galaxy over here, this was taken with HST, and prior to James Webb, this is the state of the art of what we could see of two galaxies. These two galaxies are merging. You can clearly see two nuclei, but beyond that, they look pretty clumpy. And so there is this idea that galaxies are really clumpy. They have these large clumps of star formation. There's not well-settled disks, and it takes a long time for disks to form around galaxies, like our Milky Way. But when we look at this with higher resolution, that doesn't look to be true at all. This looks like more like a disk galaxy and another disk galaxy that are colliding and getting tidally disturbed. So we can use this really good imaging to look at distant galaxies and to try to classify them. So these are all galaxies at redshift greater than 5, or no, sorry, redshift greater than 3. So we're looking at 3 to 9. For those of you who want to see the stellar mass redshift distribution, there it is. So most of our things are at redshift under 5 and lower stellar mass. The dashed line indicates the limit that we could see with Hubble. I'm going to come back to this in a second. So we're able to see fainter galaxies with James Webb than we could see with Hubble. And then we show some examples. So we classified all of these galaxies by eye. And we can sort them into various types of disk galaxies and then various types of spheroid galaxies. The advantage to James Webb is that you can see features that you couldn't see with Hubble. This first column is HST, or a Hubble Space Telescope, and then the other columns are just various James Webb filters. And as you're moving to longer filters with James Webb, you are starting to see more disks and more features pop out. So this is going to change what we think about galaxy morphology. So we can look at the fraction of galaxies with disks as we look back in time. So for these plots, you can just ignore all these. These are the various different subtypes of disk galaxies, whereas the cyan line is all of the galaxies that have a disk. The dark red line over here is all of the galaxies that are more spheroidal or elliptical in shape. And then the pink line is galaxies that have irregular features. So irregular galaxies would be the kinds of galaxies that we think are merging. And these categories are non-exclusive. And then the final category is everything that we couldn't classify because it looked like a point source. A point source could be a galaxy with a very active supermassive black hole in it. We just couldn't classify it for some reason. And so we find that we actually have mostly galaxies with disks up until redshift of 6. That's really late. That's really late in the game. That is close to like when the universe was just 1 billion years old. So galaxies seem to form disks pretty easily and pretty early. We can compare that with Hubble. So these are the exact same galaxies because we're looking at the same field, but the ones that we classified with Hubble data. With Hubble data, we had only found about 40% had disks, and that fraction really dropped off at high redshift. Okay. The reason for that drop off is over here on the unclassifiable. Just a lot of these things we couldn't classify or we thought they looked like point sources. So this had led to the conclusion that disks form late in a galaxy's life. And the very first images that weren't shown on a poster board were jaw-dropping because the thing that people noticed was that every galaxy looked like it had a disk. And so now people who do simulations of how galaxies form their disks are having to rethink that, how that happens. Okay, so the final little portion of the talk, I'm going to talk very briefly about cosmic noon, or the universe before about like from 1 to 6 billion years in age. And for this portion, I'm going to talk about active galactic nuclei. Active galactic nuclei are galaxies that host a supermassive black hole that is very actively accreting material. And this produces very luminous signatures. It can outshine the whole galaxy. So first, I'm going to talk about X-ray AGN. So again, this is the kind of stuff that Meg Urey works on. X-ray AGN are very, very bright in the X-rays because you're seeing the unobscured region of the black hole. Because of the shallowness of our X-ray data in the field that we are looking at, we actually don't have very many X-ray AGN. So for this very first AGN paper that we put out, we had 5 at redshift greater than 3. So what is remarkable about these galaxies that, again, this first column is Hubble. Look, one of them is not even detected in Hubble. But in Hubble, these galaxies all looked like spheroids, which is what we thought that these galaxies should look like. X-ray AGN typically lie in very evolved galaxies. Typically, you only see the AGN portion anyway. We didn't think that they really lie in disk galaxies. And yet, once we get better imaging, this one right here, for example, is really, really clearly a disk. That's just like kind of a beautiful disk. And in fact, they have a variety of shapes. Only one is a true point source. And I know that one's a point source because you can see the diffraction spikes on it. So the top one is a point source. Everything else lies in a resolved host. These galaxies are all massive. So again, we're talking early in the universe with masses greater than 10 to the 11 solar masses. That's huge. That's huge. Frank and I were talking about this today. How do you get a galaxy this big and a black hole this big, this quickly? And they actually happen to all be quiescent. So these galaxies are not forming stars anymore. So they have done all of their star formation. They did all their star formation in about 2 billion years. And now their X-ray is shining bright. And so what this tells us is that in some AGN, their hosts evolve really, really quickly. And so we need to understand evolutionary models for how do these things grow so fast, and that they're pretty much done by redshift 3. Okay, and so for the final little bit, I want to just introduce the MIRI data. Okay, so MIRI is where we're seeing tons of gains with NearCam too, but for my kind of science, MIRI is where we're really seeing a lot of gains. So this is a MIRI image. So this is a 5 filter image. Again, this corresponds to the wavelength of light. So we're now looking at the mid-infrared. And what is so great about MIRI is not only the sensitivity, but also the resolution, because this is Spitzer at lower wavelengths of light, and this is Spitzer in the mid-infrared. So this is kind of like, this is the data set that I wrote my thesis on, and now we have this. That is amazing. So with this new imaging, we can use this to find that obscured growth, okay? Because now we're really looking at the dust emission. We're not just looking at redshifted light from unobscured phenomenon. We're looking well into the dust emission, and so we can find the things that are obscured, that are hidden behind dust. I'm going to show you how we do it. Okay, we build spectral energy distributions. So on the x-axis is the emitted frame, rest frame wavelength of light. So this is the wavelength of light that the galaxy emitted, not what we actually observed. And then on the y-axis is how bright the galaxy is at that wavelength. The black data points show the MIRI filters. So we imaged galaxies with 6 different filters. We were able to get detections for 300 galaxies. And the MIRI field of view is actually really, really tiny. It's smaller than the NearCam field of view. And again, we're only about halfway done. And so we can look at this type of emission and we can separate, and when I say we, I mean me, whether or not it's a star-forming galaxy or an AGN. So the one on the black curve is a star-forming galaxy. These spiky features are polycyclic aromatic hydrocarbons. They are these fragile, fragile grains that live in star-forming regions. We have them on Earth. They cause cancer, stay away from them. But in space, they mean star formation. And then this emission is from old stars. And then this emission, the long wavelength at 100 microns, is due to cold dust in the interstellar medium. Okay, so my thesis work was actually making these models based on Spitzer data. And now that we have MIRI data, I have fit them to MIRI data and find out that they actually do a really, really, really good job. And then the red points are not included in the fits. The red points are from Hubble and Spitzer, and then the longer wavelength data is from Herschel. And so I fit my models to MIRI data, and then once I did that, then I overplotted the red data points, and I found out it accrues really, really well. So it's kind of amazing to look at something that you did 10 years ago and realize that it works. And then on the with the yellow curve, this is AGN emission. I know this is AGN emission because what you see here is a pure power law. You see very, very weak PAH features. This power law is arising from dust in the supermassive black hole region. So the supermassive black hole has an accretion disk around it. It's got dust that is being superheated to thousands of Kelvin, and that is emitting as a power law, and it outshines the rest of the galaxy. Now, getting to this point has taken about 5 months worth. So the only other thing that I'm going to show you on this data set is the kinds of galaxies that we have found black hole emission and star-forming emission in. So we can look at the redshift distribution of these galaxies, and the main gain here is actually at redshift of 1. I know it's not very distant in the universe, but this was where Spitzer had a real blind spot, or actually redshift 1.5. Spitzer had a real blind spot at redshift of 1.5 because you have a lot of silicate absorption in galaxies, and at redshift 1.5, it corresponded just perfectly to the 24 micron filter that you would observe at due to the redshift of the light. Anyway, and so galaxies were very faint there. So now we can finally build up a large population of galaxies at redshift 1.5. But the real gains come with the mass plot. So these masses, and I'm not going to tell you that these masses are completely accurate. This is why this isn't published yet. This is preliminary. So we're still working on making sure these masses are really accurate, and probably we're going to have to get follow-up data to do it. But the real gains come with the fact that we can see AGN or growing supermassive black holes in very low mass galaxies. And this was something when I was at Yale, I wrote a paper predicting that this was what we were going to see. And indeed, we do see it. And if these masses hold up, this is a revolutionary plot, because we have never built up a sample of this low mass that have both phenomenon in them. And these kinds of galaxies are going to inform us how galaxies smaller than the Milky Way built up their mass and co-evolved through time, which as right now is a completely open question. Okay, so takeaways. If you leave here with one thing, I hope it is that you know that James Webb was worth your taxpayer dollars. And this Christmas, I hope you tell your parents that too. It was a great investment. We are learning so much. In the first 5 months that James Webb has been working, we have already seen a paradigm shift in multiple different areas. First, we are seeing more galaxies earlier in the universe that are brighter. So we're going to have to rethink how those formed. We're finding galaxies that have really high ionization rates, but also metallicities that we didn't think they would have. So galaxies might have more dust, and perhaps every galaxy could contribute to the reionization of the universe. We're seeing more disk galaxies earlier than we thought. We're seeing really massive AGN and really massive galaxies really early in the universe. So that also requires some explanation. And we've potentially identified a population of growing supermassive black holes in very low mass galaxies where you didn't really think it was possible. So all of this is just the beginning. James Webb is just getting started. So the next 20 years, I imagine 20 years from now, we're gonna have a really different picture of what the universe looks like. All right, thank you.
There we go. Questions?
Very nice results. I guess one of the key science goals for JWST was to study dark ages and shed light on the first stars of the galaxies, and we show that there are multiple massive galaxies at high resolution. My question is, what does that mean for the realization of the universe? Is that consistent with like a high optical density? Is there a consistency check that one can make? We have learned anything about the dark ages and
Oh, sorry, I'm not going to let you off.
Oh.
They can't hear the question.
Yeah.
I'm supposed to have given him the mic.
Okay.
It's too late. Can you repeat the gist?
Sure. I believe the gist of the question is, what do really high mass galaxies, what can they tell us possibly about the reionization of the universe?
And is there tension between CMB measurements, the polarization from ionized?
Yeah, that's a really good question. I don't know the answer to if there's tension with the CMB, but I can talk about the reionization. So one of the problems up until now with reionization has been the prediction. Well, from everything that we knew about galaxies, it seemed like you needed a really, really high escape fraction of photons, and nobody had found a galaxy that had a really high escape fraction of photons, minus the green peas, but you need everything to have like 90% of their photons leaking out to reionize the universe. So the fact that we're seeing these more UV bright galaxies, like more than we thought, would help in the fact that you may not need a high escape fraction. And so that could actually resolve some tension there.
A question regarding that first part, the claim that you have detected more galaxies that are brighter than expected. You showed that ultimately you do this with abundance matching, and from that you start with a stellar mass function or function. You construct a luminosity function from, what was it, 9 galaxies?
It was 26.
I always get wickedly nervous when that happens. And my question is how do you actually do this? So I suppose you do this by just doing a 1/Vmax weighting. Is that what you do?
Yeah.
isn't one over V max weighting only allowed when there's no evolution in the number density over the range that you're observing? Because you're basically assuming you're weighting by the volume, but you're probing the area where the number density of galaxies is exposed to be evolving like crazy. And to me, it appears as V max weighting is not allowed.
Okay, so we don't have to look, it's okay. We don't have to look at the luminosity function. I know it's really small up here, but I've just plotted the surface density instead, because this doesn't have this problem of converting to a luminosity function. And so with the surface density, the top plot, well, it's actually down here too. This is what we measure. We measure the gray, and then you can see the error bars, and you can see various different models of how we model our own data. And so we can look at the surface density of these really faint galaxies, and we can compare with all of the predictions, and only the Baruzzi model matches our surface density of galaxies at these magnitudes.
So this is number density per arc minute.
Yes, this is number density, right? So there's no Vmax in this. And so even that, with just looking at the surface density, it still disagrees with the vast majority of the models.
Keep the theorists busy. It's a full employment result. Other questions? Yeah.
You emphasized early in your talk that you find a huge overabundance of massive stars at high redshift in these high redshift galaxies. Does that imply that the early universe had what astronomers would call a top-heavy mass function?
Yes, so that is the idea. That is one resolution to this, is that you have a top-heavy mass function, and so you should, because to form a star, you need to keep your gas cloud really, really cold, so that you don't have a lot of thermal pressure. The way that we cool gas clouds now is through carbon. Carbon gets collisionally excited and it radiates away the photons, and so you keep your gas cloud cool. What do you do when there's no carbon? Well, you actually can't cool your gas cloud very efficiently at all. So the original gas clouds would have been had to be much more massive to collapse, because they would have been at 100 Kelvin, whereas today our clouds are at 10 Kelvin. And so the first generation of stars should have been much more massive.
Okay, that all makes sense, but could you actually rule out that there's a corresponding overabundance of low mass stars that you just aren't seeing?
No, no. To do that, you really, right. So how would you do that? You'd build a spectral energy distribution of a galaxy, and you'd predict how each population of stars emits. The problem is that all of these models for how stars emit are based on the stars we see today. And so we don't have great models for how the first generation of stars should have emitted. So I don't know. This is a theory problem. It's not my problem. I just provide the constraints.
The next thing we want to know is black holes. Were there more black holes in the early universe than anticipated?
Yes. Well, there had to be, because they would have merged together, because most of black hole growth forms through merging.
And let me just give a shout out to Richard Larson and his student Volker Braun for having first said the overly massive stars would form originally back in the 20 some years ago. Anyway, I have a question for you, if I may.
Sure. Should we ask online too?
Oh, we could. Yeah, I don't see any hands up though, but I'll look. You talked a lot about morphology, and I have to say I'm someone who came late to the appreciation of what morphology is telling you. It isn't just a stamp collecting exercise. It's telling you something about the evolution of the galaxies. Can you just say a little more about that? Like what it's telling us and what we're learning?
Yeah. So it's telling us basically when galaxies settled down and became more well ordered, to get the disk that forms in galaxies themselves. Because we see so we see really, really early ellipticals that are massive. Those early ellipticals, if you're looking back at redshift of 5, and you have a really early elliptical, it probably formed that way. And the way that it would form that way is if you have a much denser cloud of gas that's forming stars, and it collapses much more quickly. It doesn't have time to really dissipate. And so you get stars going in random motions, whereas disk galaxies would have had to form a little bit more slowly. So you have time to settle down into and get rid of your angular momentum to settle down into a disk. But then as you build up your galaxy as well, you still need the things to settle down into a well-ordered disk. So for things like the Milky Way, we think our thick disk formed before the thin disk formed. But if you're seeing a disk galaxy, how do you form this well-ordered disk, but then also keep it as a well-ordered disk? Because disks themselves, like the spiral arms, aren't stable structures. So how do you keep that for 10 billion years? And I don't think there's great models for that.
Great. I see that Yaron had a question, which I could read half of, about, wasn't JWST also designed to do exoplanet something?
No,
I can read it to you.
Yeah, go ahead.
Do you want me to speak?
It says, my understanding is that JWST is also designed to take images and spectra from exoplanets. Are there similar surprises that have been found in the early exoplanet data as well?
Thank
okay. So no, JWST was not designed for this. The exoplanet community has piggybacked onto our telescope and they are using our time for their science. Because, and the reason James Webb wasn't designed for this is because the concept for James Webb was come up with in the 90s. When was the first exoplanet found? 1995. James Webb was already in the pipeline by then. Okay, so no, but it is being used for this. It is not the ideal telescope for exoplanets. So one of the things that it won't do, for example, is it is not going to find biosignatures on exoplanets. So they are proposing, like, the next Hubble will potentially find biosignatures on exoplanets, which is what we all want. James Webb won't do this. It's just not the right design for it. However, it can get exoplanet atmosphere spectra much better than HST did. And so those have come out. And the big surprise is that there is photochemistry happening in the atmospheres of exoplanets. So they've looked at hot Jupiters. So hot Jupiters are very close to their star. Because they're very close to their star, they've got this intense radiation field. And I really hope our exoplanet person is not listening in case I say this wrong. But because of the hot radiation field, it should destroy all the molecules in the upper atmosphere. Instead, what they have seen is carbon monoxide and sulfur monoxide, and that indicates that there is photochemistry going on in the upper atmosphere. So these molecules are forming continuously in the atmosphere. And so that's really exciting for exoplanets. I don't know, because it tells us something new about exoplanet atmospheres and how they work.
Okay, I can see we're going to have to get an exoplanet person to give a fair shake to the exoplanet science. Are there any last extragalactic questions before we close? If not, let's thank Allison again for her.
Oh, yeah.